Howdy folks, today's lesson is on exploring the periodic trends. So, we've seen some evidence of differing reactivity. In this case, what we're looking here is that we have some elements in the first group, and here we have lithium, we have sodium, and we have potassium. Lithium, sodium, and potassium. And when we put them into water, what we did is we got very similar reactions. But what we did notice is that some of them were more energetic than others. When we first initially put lithium in, what we would see is that it kind of fizzed around. There's not really much activity. But however, when we put sodium, it was explosive, but it took a little bit of time. Okay? But when we put potassium into water, this reaction was almost immediate. So what we see here is that it was a very similar reactivity, except that as we went down this group, we saw that they were more and more reactive. What's the reason? Well, the short answer, it's all about the outer or the valence electrons and how tightly they are, or it is, held by a positive nucleus. So the more tightly it's held, the harder it is to remove. Obviously, the more loosely it's held, the easier it is to remove. And we'll talk about why that is significant in a bit. So, in terms of periodic trends, there are a lot of trends that we see on the periodic table. Some of the ones that we're going to be exploring are atomic radius, ionization energy, and more specifically, first ionization energy. There are first, second, third, etc., and we'll talk about that. Electron affinity and electronegativity, just to name a few. There are a few others that we're going to be looking at, but stay tuned. So, like we said, it's all about the electron. And it's the focal point. The focal point is the strength of the attraction between the positive nucleus and the negative electron. So why is it positive nucleus? Well, remember that the nucleus is made up of protons and neutrons. Now, when we look at this collectively, the protons have a positive charge, the neutrons have no charge. So overall, if you put a positive and something that has no charge whatsoever, the overall charge is going to be positive. And if we add another proton and another neutron, for example, again, we have an overarching positive charge, and the neutrons don't really do anything in terms of affecting that positive charge. So the nucleus itself, if we were to draw our nucleus around our two protons and two neutrons, that nucleus is overall positive. Now remember that the electrons that are kind of zipping around the nucleus, they have a negative charge. So remember, back in grade 9 or whatnot, when you have a positive and a negative, they are attracted to one another. So there's some kind of attraction between this positive and that negative. And the strength of that attraction is what really dictates most of these trends. Now there are three things that influence this strength of attraction. The first one that we're going to talk about is something called shielding. Okay? And it probably sounds kind of self-explanatory, and it's not a difficult thing. It's talking about how many layers does this electron have to see through to get to feel the positivity of this proton. And in this case, it's only one layer. It's this layer right over here. So shielding is one of the things that we're going to be talking about. Number 2 is something called effective nuclear charge. And that's basically the ratio between the kind of repulsion of these inner levels and the attraction of this nucleus. And finally, the last one is basically the distance between the electron and the nucleus. Okay? Now when we mean electron, there's usually one that we're focusing on or one in question, and usually that one is the outer or the valence electron. The inner electrons don't really have much to do in terms of reactivity, at least for our level, so it's all going to be about these valence electrons. Okay, so the first factor that we're going to be looking at is shielding. Now here we have a wonderful picture of a celebrity, Justin Bieber, and the whole deal with shielding is that the inner electrons block and therefore decrease the attraction between the valence electrons, aka the outer electrons, and the nucleus in atoms with more than one shell. Okay, so let's think about this celebrity here, and let's say we have some people that have come to see him. Here are our little individuals. Now they're very attracted to this person in the front here. Hey, and they have a clear shot at him. Now let's say that they are trying to kiss him. Well, are they blocked by anyone? No, they can go right in for the kiss. Now, as other people see that he's being kissed, more people kind of flock to it, and they want their opportunity to kiss Justin Bieber. So here we have 4. Let's add a couple more people here. They're all piling in here, trying to get a kiss from the Biebs. All right. So here we have these other individuals that are coming and trying to get a kiss from Justin Bieber. But what you can notice is that since they're a little bit farther away, they have to kind of get through these people first to eventually get to Justin Bieber. Now, what are these people going to do? These inner people. Well, they were there first. They want their opportunity. They want to be closest to Justin Bieber. So if these guys get in closer, they're not going to have that same attraction or same opportunity to kiss Justin Bieber. So what they're going to do is they're going to try to push them away. They're still attracted to this individual here, but they're trying to repel these individuals here. So in a sense, what these people are doing in the center, these ones over here and these ones over here, is that they are creating a barrier for these outer folk to have to get through. And in essence, they're shielding them from what their target is. So in here we have attraction, and here we have repulsion. Attraction to the nucleus, and these inner electrons, these ones right over here, are repelling the outer electrons, which are over here. So let's bring this back into an atom. Here we have an atom of hydrogen on the left side. It has 1 proton and it has 1 electron. Now in this case, because this electron is found on the first shell, the shell closest to the nucleus, aka the 1 proton, remember hydrogen only has 1 proton, no neutrons, so it's effectively in their nucleus. This electron has unparalleled access to this nucleus, to this positive nucleus. It's not inhibited. There's nothing in between it. There's nothing in between itself and the nucleus, so it has its full attraction. Okay? But on the right side over here, what we see is that we have now a number of electrons. We have electrons on this shell here, the first shell, okay, and the second shell. Now please be aware that our first shell does not have more than 2 electrons. This is just for illustration purposes. These can be outer shells here. But what we see here is that with atoms with more than 1 shell, these inner electrons, and the inner ones are on this shell here, the inner electrons, and if there was more shells with electrons, these also would be considered inner electrons. Okay, so electrons here and electrons here. Now what you can see is that, yes, they are still attracted to that nucleus. Everything is attracted to that nucleus. Even these outer electrons, they're all attracted to that nucleus. But these inner electrons are also at the same time pushing away. Now, why are they pushing away? Electrons can't really think. Remember that electrons are negative. And if we have 2 electrons beside each other, like charges repel. So they are trying to repel each other at the same time as being attracted to the nucleus. So in this case, again, on this example here, that electron over here is pretty lucky. It doesn't have to fight with any other inner electrons to get an attraction to the nucleus. However, in this atom where we have these outer electrons, they have to fight and see through all these layers of electrons to feel the positivity of this nucleus. So what that means is that these outer electrons are more loosely, they're more loosely held. Okay? They're more loosely held than these ones on the inside. Okay? The reason being is, again, they have, not only are they farther away, they have less attraction, but also they're being repelled by these inner ones at the same time. So because the outer electrons are being repelled by inner electrons, this means that the attraction that it's feeling from the positive nucleus is less than its actual nuclear charge, the charge on the nucleus. So what this attraction is, and what it experiences, is much less than what the actual positivity of this proton or of this nucleus is. And what we call this kind of reduction in feeling or reduction of attraction is, we call it effective nuclear charge. So effective nuclear charge, or Z effective or Z effective, however you like to say it, it's the net charge that an electron feels in a multi-electron atom. So again, if we had an atom with a positive nucleus, and we have we have 2 electrons. Here we might have a couple on this side. Altogether we would have 8, and we have this 1 electron here. We're looking at what is the net attraction that this electron feels at the end after it's been kind of repelled by all these other electrons. Okay, so what is that net attraction? So it takes into account the shielding of the valence electrons from the inner electrons, and it uses this very simple formula. So Z effective is equal to Z, which is the number of protons in the nucleus, minus the average number of electrons between the nucleus and the electron of study. Now, for our purposes, our electron of study is usually going to be this outer electron here, but you could also alternatively do it for any electron in the atom there. Okay. There's also a little thing, average number. There is a way to calculate average number, but that's beyond the scope of this course. So what we're going to do is just going to use the actual number of inner electrons that we have in our Bohr-Rutherford diagram. So calculating Z effective, let's just look at our first group again, lithium, sodium, potassium. Here we have lithium and we have sodium. Now what we know is we have our Bohr-Rutherford diagrams. And in the middle here, we have our nucleus. We have 3 protons because the atomic number is 3. And we also have 3 electrons because we have no charge on the atom. So it will be neutral. We cancel each other out. Here in sodium, we have 11 protons. And again, we have 11 electrons. So let's calculate the Z effective. For lithium, our atomic number, or the number of protons in the nucleus, is going to be equal to 3. And we're going to be looking at the Z effective for this electron. So we have to figure out how many inner electrons there are. So this electron is on this outer shell here. So any electrons that are on the same shell are not considered inner electrons. They're on the same level as this one that we're studying. The inner electrons are the ones that are closest or closer to the nucleus than the one of study. So in this case, we're looking at these electrons on this energy level here. And what we notice is we have 1 and we have 2. So our S value is 2, which equals to 1. Okay? Same thing for sodium. We want to look at how many protons we have. So our Z effective is going to be equal to 11 minus the number of inner electrons. So again, we're going to be studying this outer electron for this case. So we have to see which electrons are inner compared to it. So it's the ones that are closest to the nucleus. So it's this level and this level over here. So collectively, we have 2 plus 8 gives us 10. So we have 11 minus 10, and again, we're going to get 1. Okay. So in this case, what we can see is that the effect of shielding, or the effective nuclear charge, how much this electron over here, or this electron over here, is getting an attraction, also taking into account the repulsion from these inner electrons, is pretty much the same thing. Okay? And it will be the same for all elements. Okay? It only deals when we start getting into ions that we're going to be really going to be using this Z effective, and we'll talk about that later when we get into atomic radius. So ultimately, if we try to put it together, what we see is that the farther an electron is from the nucleus, the more shielding it will encounter. Okay? Because remember, if we have a nucleus, we have all these levels, the only way that an electron can get farther is by being on a larger energy level or an energy shell. So that means that all the inside electrons all the inside shells, have to be full before it can get out there. So that means it would have to go look through all of these things and also be repelled by all of these electrons at the same time. So the farther it is, the more shielding it's going to encounter and the less attraction it has to this positive nucleus. If it has less attraction, that means it's going to be ripped off more easily. It's going to require less energy to be ripped off. So it's going to be more easily removed. However, the closer an electron is, so in the case of these electrons here, we can see that it's on the first energy level, okay, and it's very, very close. It's uninhibited. The closer it is going to be the nucleus, the stronger it's going to be attracted because it's going to have less shielding than maybe this electron out in the second energy level. It doesn't have to look through that first energy level to get to that nucleus, and it also won't be repelled by these electrons. The electrons in the front here, or that front row, have an uninhibited view of the nucleus and also don't have to go through any kind of shielding, any kind of electrons on the inner because there are none. So that means that it's going to result in a stronger attraction, and this is going to make the valence electrons, or the electrons that we're talking about in this case, these are not the valence electrons, but they're the inner electrons. It's going to make these electrons harder to remove because they're more strongly attracted to the nucleus and there's no repulsion that they have to feel from inner electrons. So the periodic trends that we're going to explore are the atomic radius. At the same time, we're going to be looking at ionic radius, so the radius of ions and how they compare to their kind of non-charged atoms, the regular neutral atoms. We're going to be looking at ionization energy, the amount of energy required to remove an electron in an atom in a gas state, electron affinity, how much basically it wants an electron. We're going to be looking at electronegativity, how much pull there is on a pair of electrons in a bonding state. And we're going to be looking at metallic and non-metallic character as well as melting point. So see you next time. Stay tuned.